Okay, suppose that we have two functions, and these are the secant of x and the tangent of x. And the tangent of x is the blue curve, secant of x is the green curve. Suppose, moreover, that we have 2 points, and we have this slider right here that goes more or less from negative pi over 2 to just under pi over 2. And we have 2 points, and the values of those 2 points are determined by the secant and the tangent of t. So this point, for example, its x value is equal to t, negative 1.07, and its y value is determined by the secant of t, or the secant of negative 1.07 radians. Similarly, this point here has coordinates that are equal to t, tangent of t. Suppose, moreover, that we define another point here, and this point, this red point, its coordinates are determined by the y-coordinates of these 2 points here. So the way it works is that the x value of this point is determined by the secant of t. The y value is determined by the tangent of t. So right now the x value here, which is about positive 2, corresponds to the y value here of this point. The x value of our red point corresponds roughly to the x value exactly actually to the y value of this point right here. So what we've defined is a curve defined parametrically, and the curve is x is equal to the secant of t, y is equal to the tangent of t, and t has a value between negative pi over 2 and positive pi over 2, and that's what we have right here with this blue dashed curve. And what we want to think about is, how do we find the derivative of this? How do we find the change in y with respect to the change in x, dy dx, given a function that's defined in terms of t? Okay, so the first thing we can do is we can look at the tangents here to these 2 points on the secant and the tangent. And so the derivative of that would give us the slope of this line here and the slope of this line here. And so we could call this derivative here, we could say, as we're talking about the x, we could say this is going to be dx dt, and the slope here is going to be dy dt. Again, tangent representing the y value, secant the x value. And so when we want to figure out dy dx, we have to use dx dt and dy dt. So let's take a look at that. So right now, we have the slope of this curve for the tangent line here at our tangent of t is given by 4.35. The slope here for our secant, which is again our x value, that has a slope of negative 3.82. So right now what we're doing is we're saying we're going to take dy dt, which is the slope here of the tangent curve, for the tangent function, divided by the slope for the secant function, which is dx dt, and that's going to give us our rate of instantaneous change, dy dt, which is going to be the slope right here of this red line, which is the tangent line for our parametric curve. So as we move t, we can see that our two slopes here are going to change, and those slopes, their quotient will determine the slope of our tangent for our parametrically defined curve. Notice that when b is set to 0, that the slope of our secant tangent line is equal to 0, which means that we do not have a defined derivative at that point for our parametrically defined curve. So again, just to look at it a little without as much stuff in the way, we have our point right here, and it has a tangent line, and the slope of that tangent line is determined by the derivative of y with respect to x. And what we said was that in order to calculate that, we figure out dy dt and divide it by dx dt. Now algebraically, dy dt, since we're talking about the tangent of t, would be the secant squared of t. For x, dx dt, the denominator would be the secant of t times the tangent of t. When we divide all that out, we get the cosecant of t. So that algebraically would be how we're figuring out how to find the slope of the tangent line here, or in other words, the derivative. But we can also just think about it as the slope of one tangent line divided by the slope of another tangent line.